In today's episode of our mini-series on what exactly is the quantum threat to Bitcoin, we're going to be covering Shor's algorithm in quantum computers. So make sure you stay tuned for today's episode. Hey everyone, and welcome back to this mini-series on what exactly is the quantum threat. In this part 2 of the video series, we're going to be touching on Shor's algorithm in quantum computers. In the first part of this series, we touched on addressing. So if you haven't seen that video, make sure you go either to this video right here that I'm pointing at or to the link in the show notes. In this part 2 video, myself and Michael Strike, who is the Director of Outreach on our team at the QRL, we're going to be quickly covering Shor's algorithm in quantum computers. So Michael, take it away.
Yeah, thanks, Ryan. The first part we handled addressing, and we talked about the difficulty of reverse factoring two large prime numbers. In other words, it's very easy to take a large prime number and a large prime number and multiply it together. That's a one-way function. It's very difficult to go backwards, and that's the difference between your private key and your public key. Let's talk about quantum computers and Shor's algorithm. Quantum computers the theory has been around for quite a while. Basically, they're if you're not sure what they are, they're state-of-the-art machines that operate completely differently using qubits rather than bits than traditional computers that we have today. Essentially, they're analog in nature. It's almost as if what's old is new again. So in order to cut to exactly what the threat is, in 1994, Peter Shor developed an algorithm called Shor's algorithm, and what it's able to do is factor in polynomial time based on a quantum computer and using a quantum Fourier transform. And what that means, in simple terms, is it's able to take that large number and be able to find those two prime numbers when multiplied together equal that private key. And that's all depending on a sufficiently powerful quantum computer. So what are the limitations with quantum computers right now? There are limitations. Still under 200 qubits. The biggest limitations right now are the engineers are trying to solve systemic noise, which is noise in the system, any type of electromagnetic radiation or interference that can touch that qubit, photon or whatever, it basically decoheres that photon and it falls apart like a blue screen on your computer. So that's one of the things, is being able to trying to separate that processor essentially from the universe is what engineers are trying to do. And if we're able to fix that the noise issue, then we'll be able to start bringing these things closer to scale. So if you're looking at the progress of quantum computers, you've got the progress moving forward. You've got progress with the qubits moving forward. You do have progress with reducing the systemic noise moving forward. And then you also have the possibility of increased efficiency for algorithms, being it Shor's or its derivatives. It has derivative algorithms that do the same thing a little bit differently. So there's also you have the increase of efficiency there. So at least things put together, essentially this is the quantum threat, being able to take that public key and be able to derive the private key from it. In a future episode, we'll talk about different attack vectors on that public key. For example, the public key in the early days is written to the blockchain. It's not written that way anymore, but it still sits in the mempool waiting for the transactions, for the Bitcoin transactions to get processed. It's sitting in RAM. So the public key is exposed until that transaction gets signed. And there's also the possibility of there's also an attack vector with a rogue node that sits there that only receives a transaction and doesn't broadcast it out and advertise it like everyone else would. It could just receive that transaction instead as a regular traditional computer. Instead of broadcasting it, it sends it to a quantum computer instead. So you have Bob here sitting, waiting for his transaction to be confirmed. It's sitting on a quantum computer because he sent it to the rogue node, and he doesn't know. So he's waiting for it to show up. It doesn't show up. Who knows what happens at that point? There's other attack vectors, but we'll cover them later.
Thank you, Michael, for covering that. I know this is a very complex topic. There's a lot that is entailed within Shor's algorithm and quantum computers. So you being able to break it down for us helps digest it. So I appreciate you covering it. And what we're going to be doing in the next video in our series is we're going to be covering our project, the QRL, and how this ties into the quantum threat to Bitcoin. So make sure that you tune in for the next video in the series, whether you're watching it right now or if you want to refer to it later, and we will cover QRL in this next episode. Thank you.